Hello everyone, let us start lecture 33. And at the end of lecture 32, we started discussing linear polarization, and where we have found out an important relation that I, which is the current density, is proportional to the over voltage, and that is possible when over voltage is very small. So, we will continue our discussion on this linear polarization and try to find out a relation which can indicate a relative corrosion response of a metal in an electrolyte. So, our discussion topic would be linear polarization and understanding a relative corrosion resistance of a metal metal in an electrolyte. Of course, relative means of course in comparison to another metal. So, now we started with this Butler-Volmar equation I 0 exponential alpha NF neta by RT this was the equation we started with, and then finally we have achieved this relation where I can be written as NF RT I 0 neta. So, this is basically the constant which is giving a linear relation, and we have also seen that if we try to plot I over voltage, so it will be linear. Now, if we see this particular equation, I can break into two terms, I equal to I 0 exponential this term these two terms we can explain, and then I can write it as I C, and of course, that time it is nothing but I applied or I circuit. So, this is so I A equal to I 0 exponential, I can write it as anodic over voltage and this is cathodic over voltage. This of course, the cathodic over voltage, and this is cathodic current density, anodic current density. Now, if I try to plot this equation not in the log scale of I, rather than absolute I with reference to over voltage, then the plot nature would be this is I positive, this is I negative. Now, this positive negative does not mean that the values are positive and negative. So, this positive negative indicates the direction. So, now if I plot eta with reference to I, and this equation gives me a plot like this. So, this is the plot pattern which indicates the plot of I applied. This is I applied. Now, I can individually check the current value, the plot of I A and as well as I C, and if we see the plot would be looking like this. Fine. So, this is I A, this is I C, and if we see this, so when neta over voltage is 0, I A equal to I C equal to I 0, and here of course I am taking the values. So, now this is I 0 also, this is I 0, but this is on the positive side and this is on the negative side. That means, at over voltage the system is reaching non corroding reversible condition, and that too also steady condition. And then as we go positive direction or negative direction in the over voltage axis, we get the individual current response. And interestingly, if you see at a high current values in this direction, at this point I A becomes equal to I applied. On the negative side, at this point I C becomes I applied. This is also understandable, because if we see the Evans diagram, we have seen that this was the over voltage plot, this was I 0, and in this case this was in the log scale, isn't it. So, that time if you see this, the plot was like this, polarization plot, and as we go upward, since it is a log scale, I could see that influence of this quantity on this will be extremely low, because this is in the log scale. So, if this becomes 10 to the power minus 2 and this becomes 10 to the power minus 8. So, the I A would be, or I applied would be equal to I A minus I C, which is 10 to the power minus 2 minus 10 to the power minus 8, which is almost equal to 10 to the power minus 2. So, that means I A becomes equal to I applied. The similar thing applies here. So, that is what a higher over voltage I individual current densities would become equal to I applied. So, this is the plot. Now, if I try to see the plot pattern when I 0 is small and when another situation I 0 is large. So, if I try to plot this I 0 is large, that case what could be the plot pattern, and when I 0 is small, what could be the plot pattern. Now, if I try to see that, so in one case I 0 is small, so the plot will be very steep, and this is I A, this is I C, and these points are I 0 values. Now, in another situation where I 0 is large, this will be much more flattened, and that case so this becomes I A, this becomes I C, and this is the I applied, and in other case this is I applied, this is I A, this is I C. Now, interesting part is, if you see this, these 2 points are also equal. This is I 0, this is I 0 2 for a second process where I 0 is large. Now, this particular plot has got a meaning. If we see this plot, let us say I have some current fluctuation in the system, this is current value I plus I negative. So, now if we have a small current perturbation, let us say this is my small current perturbation. Now, that time if you have small current perturbation, my polarization amount would be this much. This much will be my polarization amount. Let us say the same perturbation, if I give it to the case where I0 is small, this is my small current perturbation, and then potential difference would be this much. So, that means we could see that neta over voltage for del I in case of I0 large is smaller neta del I0 small. So, now that means if I0 is very large for that reversible process, let us say if I consider this process, let us say I consider hydrogen evolution reaction H plus 2E equal to H2 for this process. In one case I0 is very large, in another case I0 is very small, and now this side is indicating of H minus 2E equal to H plus, and this side is H plus E equal to H. So, this is cathodic, this is anodic process. Now, it means that if we try to design a hydrogen standard potential standard cell or a reference cell with a metal having very large I0, even there is a small amount of current perturbation because of the process that is going on. So, we could see that over voltage change, instead of writing over voltage, so I can write this. The change in voltage due to a small current perturbation in the system for this case where I0 is large, the potential is much stabler than the potential for the case where I0 is small for this situation, this case. So, if I need to design a reference electrode out of some metal where hydrogen evolution reaction will reach a steady state and non-corroding condition or reversible condition, that case I would always prefer a metal over which I0 is very large. So, that case even if I have a small current perturbation within its measurement terrain, I will not be able to have a much of change in the potential. So, if I do not have much of change in the potential, that means I will be able to measure a potential of another electrode or in another reduction or another electrochemical process with reference to this reference electrode. So, it will be a much more stable electrode, stable hydrogen reference electrode. So, that is what platinum is used while designing hydrogen reference electrode, because it has a higher I0 as compared to other metals, and platinized platina is used because it increases the I0, and once it has a higher I0, the potential becomes much more stable, and for a reference electrode we always need an electrode with a stable potential. So, it should not change with its small current perturbation within its measurement region. So, that is the importance of this particular plot. Now, if I try to see a corrosion of metal, let us say we are talking about corrosion of metal when hydrogen evolution reaction on it is the cathodic reaction, then also we can describe that corrosion process over this over voltage versus current plot. So, let us see how we are doing it. So, if I say this, So, let us say this is the hydrogen equilibrium potential. Let us say this is over voltage, and I can also term it as in the form of potential. So, this becomes E equilibrium hydrogen, and let us say this is the E equilibrium of that metal, and this would be neta equal to 0 for this reaction, and this would be equal to 0 for this reaction. So, now both of them have their own Butler-Volmer equation. Now, if I try to see the plot for this reaction, so this reaction will be plotted like this, let us say. So, this is the plot, and for metal, let us say this becomes my plot. So, this is the two plots. An individual current density plot would be like this. So, this is I0 for metal, and now for hydrogen evolution reaction, this becomes my individual current density, that means IC and IA for hydrogen evolution. So, this is I0 for hydrogen evolution, and this is the I0, the second one, this particular case, this particular case, these are the I0s for metal, this particular reaction or electrochemical process. Now, in case of Evans diagram, what we have noticed, we have to reach to a situation where I could have a mixed potential, and there. So, that means I should reach E equal to E mix, which is nothing but E core, and that time IA metal equal to IC hydrogen. So, this condition is to be met. And in case of Evans diagram, how did we do it? So, we have log I and E, we have reached to this point, and this point becomes I core equal to IA metal equal to IC hydrogen. So, that was the plot we had. So, now if I put a mirror on this particular plane, then actually what I can do, I can have a mirror image of this particular line. So, if I do that mirror image, so this is the mirror image. So, if I plot this mirror image in red color, so this will be the mirror image. And for this I can put a mirror here, and then I can have a mirror image. So, the mirror image of this, if I try to draw it with a green color, so it would be this and this. So, now I could see that they are meeting at this corrosion potential. So, then if you see this at this condition as well as this condition, IC equal to IA, here also IC equal to IA. Since this becomes IC in this case, and in this case this becomes IC, and this is IA and this is IA. So, it is basically, since the green one is the mirror image of this line. and this is the mixed potential. So, this potential becomes E core. Now, this is the plot what we get, and if I take a small overflow, so that means this will be the steady potential we will reach, steady state potential, where the rate of cathodic reaction equal to rate of anodic reaction. But remember, this is for two different processes. One is the rate of cathodic reaction indicates the rate of hydrogen evolution reaction on the metal surface, and rate of anodic reaction indicates the metal dissolution rate, and that is what we are getting this steady condition. So, now if I take a small voltage perturbation around this, so let us say this is my small voltage perturbation, which is del E. So, I can have a like this. So, now that case, let us say I term it as A, B, C. So, this becomes a triangle. So, at this, if I draw this triangle, so this is my triangle A, B, C. Now, for this I can, so this is my, let us say this is del I, and this particular point is, let us say, P. So, AP is x, let us say this particular length is x. So, then I can, so AP AC AP is equal to x, AB is equal to del I, PC equal to del E. So, these are the, so that means I can see that this axis is I positive, this is I negative, and after we leave that particular system in the electrolyte, I will reach this steady condition here. So, the polarization will be with reference to this potential. So, now that is what I have polarized it a very small quantity daily towards cathode anodic side. Now, if I try to do little bit of slope calculation. So, now I can take a slope, let us say slope of AC. So, that slope, that means this slope we are trying to measure. So, that is the slope of cathodic process slope. So, this I can write it as PC divided by AP, which is nothing but del E by x. Similarly, I can have a slope of this line to SBC, so which is the anodic process slope. So, I can write it as SC, C means cathodic, this I can write it as SA, this means anodic. So, this becomes PC divided by PB, which is nothing but del E divided by del I minus x. So, I can do little bit of juggling. So, I can 1 by del I by del E minus x by del E, and we see that this is nothing but SC. So, I can write SA equal to 1 by del I by del E minus 1 by SA, sorry, this becomes SC. So, I can write 1 by SA plus 1 by SC equal to del I by del E. So, this is one important relation, let us say equation 1. Now, I can again look at this particular picture. So now at this point, if I try to find out the slope at this point, and since this is at a very high over voltage compared to the equilibrium of potential for the metal reaction, so that means this will be close to IA. So IA equal to I applied. So now if I try to find out slope at this particular point, so that slope at C for anodic process, so that means I have to find a slope for this I equal to RT 2.303 alpha NF. So I have to find out I equal to I0 exponential alpha NF neta by RT. So this equation I have to use just to find out slope at C for the anodic process. So that case I can write this equation as neta, which is nothing but E core minus E equilibrium equal to 2.303 RT by alpha NF log 1 by IA by I0, and this quantity is nothing but beta A log of IA by I0, and IA is, I can replace IA as I core, since at this point, at this location, IA equal to I core equal to IC. This is hydrogen, this is metal, so this is metal. Now if I do d di, which will be, I can also write it as beta A 2.303 ln I car by I0. So then I can write this one as beta 2.303 1 by I core. Since I0 is constant, this is constant, this is also this entire part is constant, this is constant. So then this becomes this. So this is nothing but SA. Similarly, slope at C for cathodic process, and here one more rider is when del E is equal to small, and this is del E equal to small. So that time d neta by di would be equal to beta C 2.303 1 by I core, since neta, and this becomes neta A, of course, neta C would be equal to beta C 2.303 ln I core by I0. And remember, we are taking everything in the long term. So, and beta C, because of course we have 2.303 added, so that's why 2.303 we are taking it in the denominator. So now this is nothing but SC. So now if I put this in this equation, put these two things, this one and this one in this equation 1, so 1 by SA plus 1 by SC equal to del I by del E. So then I can write it as del I by del E equal to I core, or I can this SA equal to this. So, 1 by beta A 2.303 I core plus beta C 303 1 by I core, and here I core I can put because I C hydrogen equal to IA metal equal to I core. So, another thing is, in case of beta C we are just considering the magnitude of beta is considered, since this negative sign just indicates the direction of current flow, that cathodic current flow. So, if we do simplification, so then 2.303 I core beta A plus beta C, beta and beta C. So, then del E by del I equal to beta A into beta C 1 by I core beta A beta C beta A plus beta C, and here beta is Staffel slope. Fine. So, now this equation is a very vital equation, and this del E del I, when del E is equal to small, so that time this is considered as polarization resistance or RP. And interestingly, if we know beta A and beta C, then we can find out the corrosion current density. But even if we do not know this beta A and beta C, but doing a small experiment of fluctuating the polarization within plus minus 20 millivolt, we can get the slope for that particular linear line, and that slope gives me the polarization resistance. That means, the higher the polarization resistance, higher would be the corrosion resistance, because the more the polarization resistance, lower would be the possibility of ion formation and higher would be the corrosion resistance. So, that is what RP gives an relative behavior. So, if two metals we consider in a simple in an electrolyte, then if one metal has got a very high RP, we can definitely say that that metal has got a very high corrosion resistance in that particular solution. And if we know beta A and beta C for both the metals, then of course, we can calculate the corrosion rate in the form of I core. And how do we do it? If we get to this particular plot again, so this Butler-Volmer equation can be modified. Instead of I applied, we were having I0 exponential alpha NF by RT minus exponential. So, this was the equation we have considered. Now, there instead of I0, if we put I core, we could see that that equation is validated, because here it was I0 in this particular case, and in this hydrogen case this was the I0, but at this steady state E core potential, I could see that these two current densities are also equal. So, I could have an equation, equivalent equation for these two cases, anodic and cathodic cases at steady state E core. And then if I try to plot this one at a small over voltage with respect to this and this, so then I can, my plot would be like this, okay, and this particular voltage gap difference would be 20 millivolt, and here it is minus 20 millivolt, and then I can find out the slope at this particular point where over voltage is 0 corresponding to E chord, and then we can find out the parameter which is R p. So, this is about the linear polarization. It gives us a quick measurement of corrosion rate of a metal in an electrolyte just by measuring this linear portion of the corrosion, this Butler-Volmar equation at E chord with a plus minus 20 millivolt over voltage, and then finding slope at over voltage 0, and that would be the linear polarization resistance. Higher the linear polarization resistance, higher would be the corrosion resistance of a metal in an electrolyte. So, that is it. Let us stop here. We will now next lecture onwards, we will talk about high temperature oxidation. Thank you very much.